For this lesson, we're going to begin looking at special triangles and determining some of the exact values of some of our trigonometric ratios. So to start, we'll begin with an example. So we have a 4-meter ladder, and it rests against a wall such that the angle of elevation of the ladder is 45 degrees. How far up the wall exactly does the ladder reach? So I'm going to begin by drawing a diagram. So here's my wall and the floor. Now it's safe to assume that when I have a wall connecting with the floor, that we have a 90-degree angle there. Now I have a ladder leaning up against this wall like this. And now I can put in my values. So we know that the ladder is 4 meters long, so I can label that. Next, we're told that the angle of elevation of the ladder is 45 degrees, so I can put that in here. And we're trying to determine how far up the wall the ladder reaches. So I'm going to quickly draw my triangle separately over here outside of the diagram, just so I have a better look at my triangle. Now, since I have a right angle triangle, it means that I can use my primary trig ratios. So I start by circling my angle, and then I'll label my hypotenuse. So my hypotenuse is across from my right angle. Then my opposite side is right across from my given angle. So because I have values for opposite and hypotenuse, we can use sine. So I'm going to write sine theta is equal to opposite over hypotenuse. Now in this case, our theta is 45 degrees. X is on the opposite side, and our hypotenuse is 4 meters. So because we're looking for x, we're going to isolate the numerator. So we'll start by multiplying 4 on this side, multiply by 4 on this side, and we have 4 sine 45 degrees equals x. Now the question requests an exact answer. Now, if I put this into my calculator, I'm going to get a long decimal. So this is really as exact as we can go. But it's very, very challenging here to get an exact answer from this and to compare it to other answers. So that's why we start using special triangles and determining some exact values. So what we're going to do is we're going to look at 2 specific special triangles that will give us some exact values for 3 different angles. So the first special triangle that we need to know is our 45-45-90 triangle. So we're going to consider a right isosceles triangle where the 2 equal sides have a length of 1 unit. So if you look here, we have 2 equal sides, both with a length of 1 unit. Since this is an isosceles triangle and has 2 equal angles, both of our angles here must be equal to 45 degrees. This is because the total interior angles of a triangle equal 180 degrees. We've used up 90 with that right angle triangle, and then we split the other 90 between those equal angles, so 45 each. Now we need to find the length of the hypotenuse. So to do that, we label our triangle. C has to go onto the hypotenuse, and A and B can go onto the other 2 sides. So now we can sub everything into the Pythagorean theorem. A squared plus B squared equals C squared. So A is 1, B is 1, and we're looking for C. So we'll have 1 plus 1 equals C squared, 2 equals C squared. So that gives us root 2 equals C. Now this is our first special triangle. And what we can do with this special triangle is we can find exact values for our ratios for the angle 45. So that's exactly what we're going to do. I'm going to draw the triangle again down here just so you can see it as we work through things. I have 1, 1, root 2, 45, 45. Now we're going to use this triangle to determine all of the above values: sine 45, cosine 45, tan 45, cosecant, secant, and cotangent, all of 45. So to do this, we have to label our triangle. So the first thing I'm going to do is circle one of the angles. It doesn't matter which 45 you circle because they're both the same angle. Now the side across from my right angle is my hypotenuse, and the side touching my angle is my adjacent. The side across from my angle is my opposite. So now using this, we are going to find all of our exact values. So sine 45 is opposite over hypotenuse, like that. Now we don't like to have radicals on the bottom, so I'm just going to multiply like that. So we'll have root 2 over 2. For cosine 45, we have adjacent over hypotenuse. So that will also be root 2 over 2. For tan 45, we have opposite over adjacent, so 1 over 1, which is equal to 1. Then for cosecant 45, we have hypotenuse over opposite, so we have root 2 over 1, which is equal to root 2. For secant 45, we have adjacent over hypotenuse, so root 2 over 1, root 2. And for cotangent 45, we have adjacent over opposite, so 1 over 1, which equals 1. Now all of these special angles are going to be your exact values anytime you're asked about tan 45, cotangent 45, etc. That's our first special triangle. We actually have two. So the second special triangle is our 30, 60, 90 triangle. And this triangle can be used to determine the exact values for 90 and 60. So we're going to do the exact same thing that we did above, but for 30 and 60. So to start, I'm going to draw that triangle again. So the given one. So for this specific triangle, we have 60 degrees up here, 30 here, our 90-degree angle, 1, root 3, and 2. Now because I'm looking for 30, I'm going to circle the 30, label my hypotenuse, my adjacent, and my opposite. And now I go through and find all of the values of sine, cosine, tangent, cosecant, secant, and cotangent. So sine will be 1 over 2. Cosine will be root 3 over 2. Tan will be 1 over root 3, which equals root 3 over 3. Cosecant is hypotenuse over opposite, so 2 over 1, which is just 2. Secant is hypotenuse over adjacent, so 2 over root 3, which is equal to 2 root 3 over 3. I'm just getting the radical off the bottom. And cotangent 30 is equal to adjacent over opposite, so we have root 3. So all of these are your exact values for 30 degrees. Finally, we're going to do the same thing for 60 degrees. So I'm going to draw out this triangle again. 30 degrees, 60 degrees, and 90. 1, root 3, and 2. Because I'm looking for 60, I circle 60, and I label my triangle. So I have my hypotenuse, my adjacent, and opposite, and then I find all of these values. So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tan, opposite over adjacent, which is just root 3. Cosecant is hypotenuse over opposite, which is 2 root 3 over 3. Secant is hypotenuse over adjacent, so we'll have 2 over 1, which is just 2. And then cotangent is adjacent over opposite, which is root 3 over 3. So these are all of your special values for 60. Now we can use these values anytime I see sine 60, cosine 60. I can immediately just put this number in as the answer, and then I'll have an answer without rounding. So now we're going to go through some examples of how to use this. So, for example, we have sine 45, cosine 45, plus sine 30. So what I'm going to do is I'm going to look at all of the values above and fill in the exact values for sine 45, cosine 45, and sine 30. So we'll have root 2 over 2, root 2 over 2, plus sine 30 is equal to a half. And now I'm just going to simplify that. So we'll have 2 over 4 plus 1/2, and we can simplify that fraction. 1/2 plus 1/2 equals 1. So using my exact values, I could find that that equals 1. Now here's another challenging example. We have sine 45 divided by cosine 30. So to start, I'm going to rewrite it like this. And the reason why I'm doing that is so that I can work with fractions a little bit easier. So sine 45 is equal to root 2 over 2. And we're going to divide that by cosine 30, which is root 3 over 2. Now, when we divide fractions, we flip the second one and multiply. So we'll take our first one, flip the second one, and multiply. So our 2's cancel here, which is nice. And we're left with root 2 over root 3. We don't want that radical on the bottom, so we multiply by root 3. And we have root 2, root 3 over 3, which we can simplify to root 6 over 3. And that's our final answer. But you can see how we use those exact values to sub them in, and then we just simplify them using our rules for radicals. Now, the other way that this is useful is I can use this backwards as well to find angles. So, sorry that there's sine written here twice. You can just erase one of them. So we have sine theta equals root 3 over 2. So then what you're going to do is look through all of those exact values that we put together and determine for which angle sine is root 3 over 2. When you look through all of your other angles, you'll find that the only one where sine is equal to root 3 over 2 is 60 degrees. For this one here, we have root 3 tan theta equals 1. So first we'll start by trying to isolate tan theta. So we'll divide by root 3 on both sides. So we have tan theta equals 1 over root 3. So then what we'll do is we'll get that radical off the denominator, and we'll have tan theta equals root 3 over 3. So now what you're going to do is you're going to look through all of the special angles above and determine where tan theta equals root 3 over 3. And when you do that, you'll find that theta must be 30 degrees. And that's our final answer. Now we have one last example that is a little bit challenging, but it's another important use of our exact values. Now I fixed the diagram on the right, but for some reason it printed wrong. So just be mindful of that and just adjust your diagram to look the same as the one on the right. So what we're given about this triangle is we're given the location of angle alpha, angle beta, and angle 45. We're also told that cosine of alpha is root 3 over 2. Now what we're trying to determine is the exact area of this triangle. So to find the area, we're going to have to fill in base times height divided by 2. So we'll need to determine the height. We need that value. And we also need the base as well. So let's start by trying to figure out what we can use. Cos A, or cos alpha, is equal to root 3 over 2. So we're given that cosine of alpha is equal to root 3 over 2. Now we know that for cosine, our ratio is adjacent over hypotenuse. So if I circle my angle alpha, this cosine value gives me my adjacent side, root 3, as well as my hypotenuse. So what that's done is it's given me my value for my height. My height of my triangle must be root 3. Now we also need to find the base of this triangle, because we need to find both this side of the base and the other side of the base. So to find this side of the base, I can use my Pythagorean theorem. So what I'm going to do is I have C, A, and B, and I'm just going to solve for B. So A squared plus B squared equals C squared. So we'll have root 3 squared plus B squared equals equals 2 squared. So we'll have 3 plus B squared equals 4. And then we'll move that 3 over. B squared equals 1. Square root both sides, and we'll get B equals 1. So that means from here to here, we have 1. Now, for my second part of the triangle, in order to determine that second part of the base, we need to use that beta, 45, and root 3 in order to determine the full base. So, if 45 is that angle, I can determine this angle here. So we have 180 equals 90 plus 45 minus plus beta. And then we have 180 equals, and then we'll add 90 and 45. Which gives us 135 plus beta. Then we'll subtract that from the other side, so we'll get 45 equals beta. Now, this triangle with two 45s looks a lot like our special triangle. And in addition, if I have two 45-degree angles, just like above, this has to be an isosceles triangle. It has to be. It's the only way that those two angles will be equal. So that means right here will have to be root 3 from here to here. So now we have our height and our base, so we can find our area. So area equals base times height divided by 2. My base is equal to 1 plus root 3, and the height is equal to root 3 all over 2. Now I'm just going to distribute in that root 3. So we'll have root 3 plus 3 over 2. And that is our final answer.